everyone, and welcome back to this series on intermediate statistics. Today we're going to be continuing our exploration of variable analysis and discuss a method known as the sum of squared analysis method, sometimes also called the ANOVA sum of squares, that can be used in order to assess the particular contribution of predictors. So let's assume that we have this multiple linear regression model, beta 0 plus beta 1x1 plus beta 2x2 all the way down to beta pxp, where p is the number of predictors inside of your model. As we already know, there are several different ways of assessing the appropriateness or the suitability or the fit of these particular parameters for these response variables y. But ANOVA sum of squares, in particular SST, is equal to SSE plus SSM, and building f-test statistics, assuming the normality and independence assumptions are met, is a very common way to do so. So in case you aren't familiar with these particular metrics, the SST can be calculated by doing the sum of your particular y values associated to their means. The SSE can be found by doing the sum from k is equal to 1 to n of your particular y values minus their predicted values squared. And again, that sum also ranges from 1 to n. And then we have another sum of squares, the SSM, which can be found by doing the sum from k is equal to 1 to n of our predicted values, y hat k minus y bar the quantity squared, and one can show that these sums do add up to one another, i.e. SST is equal to SSE plus SSM. So what exactly do these particular components mean? Well, the SSM can be viewed as the portion of the variation that is captured by these predictors. So we can say that this is the variation captured by our predictors, which is pretty much our model. And then we have SSE, which is the variation not captured by our model. And then our SST is our total variation, right? So total variation is partitioned, one could say, into the amount of variation that is not captured by our model and the variation that is captured by our particular model. Obviously, we would like our SSE to be minimized. That's how these betas are constructed via the least squares approach. But we don't want it to be extremely close to zero, else we have evidence that our model has been overfitted. And if there is some variation that our data does not encapsulate, our model will not be able to pick up on that in that particular case. So that's all fine and well. But there's one natural question that one could ask, because all of our predictors are contributing to this particular SSM. So one could ask is, what portion of our SSM in our model is contributed from each of our predictors x k, let's say, where k ranges from 1 to p. So this particular question, what portion of the SSM, is sometimes referred to sum of squared analysis, sum of square analysis. Some people also call it an ANOVA sum of squares, but generally speaking, I prefer to call it the sum of squared analysis because we're in particular focused on the SSM and the things that are contributing to it. Usually ANOVA sum of squares is just focused on your SSE, SSM, MSE, MSM, and the quotient of the two, building an f-test statistic. Right? So sum of squared analysis is going to be focused on our SSM metric. So we're going to see if we can partition that SSM into, for example, SSM for variable 1, SSM for variable 2, SSM for all the way down to variable p. Right? So for our discussion, what I'm going to do is I'm just going to be using a very pedagogical model. Let's assume y is going to be representing happiness, and let's assume that I want to use x1 to be age to predict happiness. Let's assume that we want to use another predictor x2 that's going to correspond to height, and let's assume that we have a third predictor. Let's just keep things very basic. Let's assume that that's your average sleep per night. Let's assume that you've already calculated a data set of size n that has these three predictors and y response variables. So we have p responses, p is equal to 3, and 1 y response for our multiple linear regression data set. And let's assume that we've already ran our least squares regression. And let's assume, for the sake of this example, so let's assume that we obtained an SST, which came out to 1260.6. Let's also assume that the SSE for that particular model came out to 1232.9. And obviously, if SST and SSE are these values, then one can find that the SSM is equal to 27.7. So one can see that the SSM is not that big, which means that when we do the MSM over the MSE, that is going to not be so large, right? Because usually when SSE is close to 0, that's going to make your f-stat extremely large, forcing your p-value to be extremely closer to 0, causing you to reject the claim that these coefficients are close to 0, right? So obviously our SSM is not as large as we would hope in order to prove that our model is working for predicting these particular y values, but of course it doesn't necessarily mean that you can't perform a sum of squared analysis on those coefficients, even if those coefficients appear to be potentially useless, right? So let's just work with these numbers and sort of see what comes from it, right? So let's restate the question that we seek to ask. So what portion of our SSM is associated to our x1, x2, and our x3. And let's sort of see a few ways of how we're going to answer that question. So the method that I want to introduce first, that's actually quite easy to implement, sequentially adds each variable one by one and looks at the percentage for which the SSM increases on each of these iterations. So let's actually walk through this example and sort of see how that would look like. So the first thing that we want to do is, first off, let's take our model y and let's regress it against x1 only. So let's pretend that for this particular data set, we see that the SSM for this particular model came out to 17. Let's also pretend that the SSE for this particular model came out to 1243.6. Then what we're going to do is we're going to take x1 and then union x2 inside of that model. So now y is regressed against x1 and x2, so we went from simple linear regression to multiple linear regression. Now, keep in mind, every time you do add a variable, your SSE will always be less than it was before, and your SSM will always be more than it was before. So SSM is going to guarantee to increase as long as the coefficient for our new variable is non-zero. So in this particular case, let's assume that our SSM is going to be equal to 23.2, right? So obviously it increased, and let's pretend that our SSE also decreases in a similar manner. In particular, this would go to 1237.4. Keep in mind, SSM and SSE increase and decrease by the same magnitude because SST stays fixed. And lastly, let's assume we regress y against all three variables, x1, x2, and x3. And this is going to be the same as we had before. So SSM is going to be equal to 27.6, and our SSE, again, for that particular full model, was 1232.9. Right? So as we clearly see, 17 increases to 23.2, and 23.2 increases to 27.6. Right? So let's also assume that for the sake of our next table that we want to say, if y is regressed against no variables, against 0 variables, we will say that the SSM for that particular case would be 0. Okay, so your SSE would be equal to your SST. All right, so let's look at our table so we can organize all our results. So we have our SSM which we're modeling, and then we're going to have the number of x's in our particular model, and then we're going to look at the change in the SSM over our addition of these variables. Right? So we're going to start off with 0 variables, then we're going to have 1 variable, and then we're going to have 2 variables, and then we're going to have our final 3 variable value. For the number of x's, obviously since we have none, then our SSM will be equal to 0, and there's no delta to calculate since there's nothing before 0. And then for 1, in particular variable x1, then we saw that the SSM went up to 17. So the change from 0 to 17 was equal to 17. And then for 2, we had 23.2, and again that's for x1 and x2. And the difference from 17 to 23.2 is just 6.2. And then from 2 variables to 3 variables, which was x1, x2, and x3, our SSM, of course, increased up to 27.6. And the difference between 23.2 and 27.6 is only 4.4. All right, so we have these numbers 17, 6.2, and 4.4. So obviously our model's SSM increased the most for x1. Sometimes looking at these delta SSMs in their original form can be a little bit tricky. So sometimes we would look at the percent change. So the percent change in SSM. Okay, so what we're going to do is we're just going to take our SSMs that we get in terms of deltas, and then divide that by the total amount of SSM. Right? Because, keep in mind, our total SSM goes from 0 to 27.6, so we're going to be using 27.6 as our comparison. So for example, again, that's not going to have any value or contribution, so we're going to have 17 all over 27.6, we're going to have 6.2 all over 27.6, and then we're going to have 4.4 all over 27.6, and keep in mind, those ratios will always sum up to 1. So if that is the case, then what we're going to have here for percentages is approximately 69.1%, and then we're going to have 22.5% for the next, and then 15.9% for the next, and everything ranges from 0 to 1 in this case, so you can start to make some arguments about which one is contributing the most. So from this table, we clearly can see that introducing x1 into our model first gives us the largest change in our SSM. So the next question that I want to pose to you, so is x1 contributing the most? So I want you to take a moment, maybe even pause the video, and think about, can we interpret this 69.1%, since it's bigger than the other two, as justifying that x1 is really contributing the most to our multiple linear regression model? So before I reveal the answer to this very potentially tempting to answer question, I want to mention one thing that we may have taken for granted. In particular, when we defined our x1, x2, x3, we had 3 different variables, for example, age, height, and sleep per night, but we could have assigned them to any variable in any order. For example, we chose age for x1, height for x2, and then sleep for x3. But we could have assigned age to x2, height for x3, and then sleep for x1. If that is the case, when we introduced x1 into our model first in order to calculate our percentage change in our SSM, sleep could have been, the first variable to enter the model. So the natural question is, would that change still be 15.9% if we were to replace it first? And would our next percentage change be our 69.1? And would our last change bear 22.5%? Well, naturally it may seem, okay, yeah, maybe that is the case, but let's actually experimentally, just check that out and see if that is actually the case. So before we actually experiment with that, pretty much what we're sort of looking at is, does order matter for this sequential sum of scores analysis? If it does matter, then that means we would have to technically consider all possible hierarchies of our variables, because our first hierarchy was x1, x2, x3, where we're going to keep consistent with x1 age, x2 height, and x3 sleep. But you, of course, that's not the only hierarchy you could consider in order. You could do x1, x3, and x2. You could start with x2. You could also start with x3, giving you x1, x3, or x3, x1 following. And, of course, you could do x2, x1, and start with x3, x1, x2. So in this particular case, since you're not allowed to repeat variables, there would be 6 possible hierarchies you could assign to your predictor values for your model. In particular, there's going to be 3 for the first, 2 for the second, and 1 for the third by default, and hence there's going to be 3 factorial different types of hierarchies for your 3 predictors. So if that is the case, let's try and answer, does the order matter? And even if we do get different percentages in SSMs, will we still get the same ranking in terms of contribution for these variables? So what I want to do is I want to just create another table, and instead we're going to be introducing x2 first, x2 being height, and then we're going to follow up with x3, and then we're going to end with x1. So x2, x3, and x1 in that particular order, right? So these are going to be our models of interest. And then we're going to look at our SSM. Obviously, we're going to be coming from an SSM of 0 if we have 0 predictors. Okay, so SSM for this, let's assume, is going to be 1.6, 11.3, and 27.6 respectively. Keep in mind, 27.6 will be the same as long as you have all 3 predictors introduced from the same exact data set at the very end. And of course, there would be associated SSEs for each of these, which you should be able to calculate as, for example, 1259, 1249.3, and 1232.9. And again, that SSE will be the same as the full model, regardless of the order for which you introduce them. All right. So if that is the case, what is the percentage change in the SSM? So the percentage change in our SSM, because this is how we're going to establish our ranking for contribution. So if we look at these percentage changes, we're going from 0 to 1.6, so that's going to be 59.1%. And then we're going to go from 1.6 to 11.3, and that's going to be given to be, actually, no, we're going backwards, right? So actually, let's do delta first. Let's do delta first. All right, so delta SSM. So delta SSM, 0 to 1.6, that's obviously just going to be 1.6. 1.6 to 11.3, that's obviously going to be 9.7. And 11.3 to 27.6, that's going to be 16.3. Right? And then we're going to take each of those and divide by our total SSM. So we're going to divide by 27.6, divide by 27.6, and divide by 27.6 to get our percentage changes. Right? So our percentage changes, let's assume that we're just focusing again on x1, x2, and x3. The only difference is x1 is going to be coming from our last cell. That's where our 59.1% is going to come from. Our x2, when we introduce that, well, that's obviously going to be first, and you can find that to be 5.8%. And then when we introduce x3 next, that's going to be our second introduction. So that's 9.7 over 27.6, and that's going to be 35.1%. Right? And that's if we do an x2, x3, x1 hierarchy for our particular models. And we can look at our hierarchy of x1, x2, x3 to sort of recollect whether they were the same exact variables. And if you remember, this was 69.1%, this was 22.5%, and this was 15.9%. So do they still have the same exact ranking in terms of contribution? Obviously no. But one thing is very interesting is x1 appears to be the largest across these two hierarchies, but x2 and x3 do swap positions in terms of ranking, right? So you cannot trust sequential sum of squares directly because it obviously depends on the order for which you introduce them into the model. So obviously we do have some information coming from sequential sum of squares, but when order matters, then comes a couple natural questions or a couple points that we need to keep in the back of our mind in case this is the method that you want to discuss. So overall, this method, as I've already called it, is called sequential sum of squares. And this is a sum of squares analysis, and some people also call this a type I sum of squares analysis. So what have we observed so far about sequential sum of squares? Obviously, it depends on the order of introduction, which then begs the question, which one to trust? And one could say, okay, maybe I could calculate all 6 factorial different types of hierarchies, look at the percentage changes, and then average all those percentage changes, and then I can get from there. But again, that could be potentially misleading. So another approach, which I will introduce, is sometimes or can be referred to as the full reduced model comparisons. Full reduced model comparisons. And if you've ever learned about partial f-test, then this should sound a bit familiar to you. And we're going to also refer to this as type 2. All right, so what exactly is our full model? So our full model is going to be the model containing all of our predictors. So that's going to be y regressed against x1, x2, and x3 all at once. So obviously it doesn't really matter the order. And as we've already observed, the SSM for this pedagogical data set came out to 27.6. All right. So what we're going to do is we're going to remove these variables 1, and then 1, and then 1. So for example, we're going to look at x1 removed, and then we're going to look at x2 removed, and then we're going to look at x3 removed. So we're going to look at our reduced models. So our reduced models, and see what our SSM turns into when you remove these particular variables. Right? So in particular, if you remember, for example, from AV plots or partial f-tests, the model that we're going to be interested in is y regressed against x2 and x3. This is going to be y regressed against x1, x3, and this is going to be y regressed against x1 and x2. So obviously you can easily calculate the SSMs for each of those particular models, and one can find that this is going to be equal to 11.3, 20.2, and 23.3, let's say. And then we can calculate the change in SSM, and one can find this is going to be equal to 16.3, 7.4, and 4.4, respectively. Right? And keep in mind, when we're looking at the percentage change, we're looking at what our SSMs were with respect to our full model, what our SSM is with respect to the full, and what our SSM is, again, with respect to the full. So we can then look at our percentage change. So our percentage change in SSM by looking at our particular values divided by our total SSM of 27.6, and that will tell us similar information as was before. So in this particular case, one can find that this is about 59.1%, and then we're going to have 26.8%, and then 15.9%. Right? As you can clearly see, x1 still is having the larger one, x2 is now the second largest, and third is the third largest, or the smallest in this case. But before we proceed, I just want to mention that the sum for these is not equal to 100%. Right? So why would these percentages not add up to 100%? Well, we're not considering that, when we remove x1, we're also removing a bit of influence of x2, or some of x1's influence is still remaining inside of x2 and x3. So when you see this, sum not equal to 100%, you can ask the question, do they overlap? Right? And obviously looking at the individual predictors, we should already know, is not necessarily trustworthy because they could consider or could contain interactions or dependencies within our data, even if it is by chance. right? And that's why you shouldn't just look at the beta coefficients and their magnitude from 0, even if it is in the standardized realm, right? But nonetheless, it does give us some notion that we don't have to focus on the order for which we remove compared to sequential sum of squares, right? So even in this case, we see, okay, maybe x1 is really contributing to our particular data. But it does not consider this overlapping issue, right? So even if it does not add up to 1%, it still captures, it does capture the percentage contribution roughly if they were not interacting. Right? So it doesn't matter the order, but they could be interacting, and this particular model does not necessarily consider that. Right? So what do you think a type 3 sum of squares analysis method will look like? You may want to pause the video and sort of think of how that would play out. So the next sum of squares analysis method can be sometimes referred to as the full reduced model comparisons method with polynomial and interaction terms included. And I'm going to be referring to this method as type 3 sum of squares analysis. So what exactly will the full model be in this scenario? So again, we're going to be considering x1, x2, and x3 inside of our model. And then we're going to be including some polynomial terms. For example, x1 squared, x2 squared, x3 squared. You could also go up to cubic or quartic if you wish. But let's just stop at quadratic. And then we have x1 and x2 multiplied, x1, x3 multiplied, x2, x3 multiplied. And let's also do our x1, x2, and x3 all multiplied together. Right? So these are our base variables, or predictors, and then we have our polynomial terms, and then we have our interaction terms. So our x1, x2, x1, x3, x2, x3, that's obviously going to be our first order interaction terms, and since we only have 3 variables, that means we are only going to have 1 second order interaction term because it's 1 variable with respect to 2. All right, so this particular model is what we're going to be referring to as our full model, right? And what we're going to do is we're only going to remove our base variables. So we will only remove our x1, x2, and x3 for the reduced quote-unquote models. All right. So let's assume that once you actually use the same exact data as we were doing before for our full model, let's assume that the SSM for this particular case is 318.4. Right? And of course, you could look at the SSE for this particular model, and let's pretend that that's 942.2. Right? And obviously, since we're including several different variables, we have 3 plus 3 plus 3 plus 1. Obviously, that's going to have our SSE tend to 0. So let's also assume that we are not overfitting. That is, you've performed all of your explanatory variable analysis and your model analysis to assume that we're actually not overfitting, that this model is indeed appropriate for your data. So once you have your full SSM, now we can get our partial SSMs and then analyze from there. Right? So for our model, we're going to take our full model and take away x1, and then we're going to have our full model and take away x2, and then our full model, and then we're going to take away x3 in each of them. And then we're going to be calculating our SSM as usual, our change in SSM, and then we can get our percentage contribution to our model as well. Right? So let's see for this data set what it actually comes out to and see if we get any spooky math. So for SSM, or for when you remove just x1, you're going to have 278.5. Obviously, it has decreased. And then 281.8, 279.9 for your individual SSMs. And then obviously you're going to be comparing each of these values to our original SSM to calculate your deltas. So this is going to be equal to 39.9, 36.6, and 38.5, right? So then we're going to calculate the percentage of SSM that is associated to each of these delta SSMs. So 39.9 over 318.4, 36.6 over 318.4, and so on. And that's going to give you 12.5%. So 12.5%, 11.5%, and 12.1%. And if you add up these little percentages, then what you're actually going to get is a total of 36.1% of your SSM is contributing to x1, x2, x3. Now, where is the rest of this SSM located? Well, obviously, it's going to be located to our polynomial terms and our interaction terms. So since this is substantially less than 50%, let's say, then we have evidence to believe that maybe our model is not entirely linear or our variables are interacting with each other. Right? So these percentages are not necessarily meaningful. Nonetheless, we can say that x1 is potentially contributing a little bit more than x3, but usually since it doesn't add up to 100%, it's usually hard to interpret these in their raw form. So what we instead would do, so this is obviously our total contribution with respect to everyone. Usually we would only like to look at the relative contribution with respect to each other. So you take each of these objects and we divide them by our 36.1%. So you get a bunch of percentages that indeed always add up to 100%. When you do that, you're going to have 34.6%, you're going to have 31.9%, and then you're going to have 33.5%. And obviously that's always going to total up to 100%. Right? So from this particular table, what can we see? So we see that x1 is contributing more than x3, and that's contributing more than x2. Right? At least from this particular table. If you look at some of the other tables, then you might have a different conclusion. Right? So we've discussed three different ways of performing a sum of squared analysis for analyzing this particular problem. You know, what percentage of the SSM is contributed from each of your predictors. So let's sort of summarize these out in a little organization table. So type 1. So that's the sequential sum of squares, and obviously this is good if you already have a hierarchy of your variables. Like if you're dead set on including one variable before the other, or one's more important or relevant in terms of the study that you're doing, definitely sequential sum of squares does have a place for you in this particular story. So type 2, which is where we take our full model and just remove one after another. If you have collinearity, then type 2 will be an issue for you. Right? Especially if linearity is not met. Especially if linearity is not met, right? And obviously, if you're using type 2, that means you don't have a specific hierarchy in the back of your mind. And then type 3, useful, obviously, for more complex models. So generally speaking, if you don't know a hierarchy that's meaningful for your study, or you aren't sure if collinearity is met or if your variables are interacting with each other, type 3 is definitely the more general open one for your particular study to go to. But of course, you can't say that type 3 is the best because, you know, type 1 and type 2 do have their components, right? Because your variables shouldn't interact with each other. You shouldn't have non-linearity issues with your model. So type 2 should be working, but type 3 is a little bit more safer. Right? So that's how, 3 different methods that you can use to sort of rank your variables in terms of contribution, which also added variable plots does as well in its own unique way. So I hope you enjoyed this video, and I'll see you in the next one. Take care.